All right, today we're going to start section 4, derivatives as a rate of change. Remember we started earlier this semester discussing rates of change, the average rate of change, the instantaneous rate of change. That was in chapter 2. Now we're going to use derivatives to describe rates of change. And typically, when we were talking rates of change, we talk with respect to time. But you don't always have to do it with respect to time. You can do it with respect in business with respect to how many things you produce or how many things you sell, how much it costs, how much your money you're getting in. So it doesn't have to be with respect to time. So the first thing we're going to look at is instantaneous rate of change. In chapter 2, we discussed this with the difference quotient. Which was f of x plus h minus f of x This was defined as the average rate of change but what this represents is remember all this stuff is actually finding the slope. So what this is looking for is between an x, x1 and x2. This is our distance h. So that's x1 plus h. So x1 is just itself. X2 is x1 plus h. It's the difference between the two. Y1 is the same thing as f of x1. Y2 is f of x2, which is f of x1 plus h. So what we're looking for here is going from x to x plus h. We're looking at that interval. And eventually, as h goes to 0, you get the same point. Then we have the rate of change at a given point. Okay, here's the definition, the formal definition. The instantaneous rate of change of function f with respect to WRT x at any x sub 0 is the derivative of f. So if the average rate of change was this, was the difference quotient, then when we add up all the pieces and set h equals to 0, so now we have our limit. As h goes to 0 of our function. So here's one of the formulas we'll be using for the instantaneous rate of change. So what does this tell us? What is this part? That's the average rate of change. So if we take the limit of an average rate of change, then we have the instantaneous rate of change. So the instantaneous rate of change is equal to the limit as h goes to 0 of the average rate of change. Okay, ready for an example? Here is an example. The area A of a circle is related to its diameter by the equation A pi over 4 times the diameter squared. How fast does the area change? How fast does the area change with respect to the diameter when the diameter is 10? Nope. Because this is the area of the circle. We want the change. And change occurs when what? We take a derivative. So we have to find A prime. Pi over 4 is a constant. We're taking it with respect to the diameter. So pi over 2 times d. So when the diameter says when it's 10, so A prime of 10 is it changes, the area of the circle changes by 5 pi, whatever units we're looking at. That's the change. Example 1. Now let's look at motion problems. Along a linear path. We're going to look at 4 things. Displacement, velocity, speed, and acceleration. Since we're talking about acceleration also, there's a fifth one we talk about. It's called a jerk. You probably felt a jerk when you're driving, and all of a sudden your car just like that. And we'll discuss what that is in a second. So displacement is simply a changing of positions. We use S to describe our displacement, and S is a function with respect to time. So the displacement of an object over time t over the interval from t to t plus delta t. Because that's what we're always, this is our h. It's the same thing we had with x plus h. So our h is the change of x. Here we have time, so we have change of time. Where the change of our displacement is f of that minus f of t. So it's the distance, it's the difference of our two positions. Or if we were here and here we're here, remember, this is f of t1, this is f of t2. And time here to time plus delta time. So this is how come this is f of t plus delta t. So figuring out the difference of the two tells us how far we moved. So with this, the average velocity, how does velocity relate to displacement, our position? Our average velocity of the object over time interval t to t plus delta t. So the average velocity is velocity over the displacement divided by time traveled. So what is our displacement? Our displacement is delta S. And time traveled is from t to t plus delta t is delta t. So up here, S is defined as that. So our formula is t plus delta t minus f of t divided by delta t. That's our velocity, our average velocity. Remember, this is the average velocity. How would we find it at an instant? What do we have to do to find it as an instant? Yeah, we have to take the limit of this with respect to delta t goes to 0. So yes. So the difference quotient is our average velocity, average displacement, whatever. Where for that yet? No. But now what is speed? We talked about displacement. What is speed? It is a rate. Yes, it is a. What kind of? How does it rate? How does speed relate to displacement? Well, because how fast is speed? So speed is how fast. Yes. So it's how far you moved over a given period of time.
Yeah, that's right.
Yeah, it's just that you can't use fast with speed because it means the same thing. It's the change of displacement over time. So speed is the change of the displacement over time. Okay, so how are displacement and speed really different? Displacement is your position. So if you started here at point A, that's your home, and you go to school, let's say that's 10 miles, and you go back, how far did you travel? The 10 miles also. They're each the same distance. But when it comes to speed, if I went from point A to point B, as opposed to point B to point A, they're going different directions. So because they're going different directions, I now have a positive and negative. So if I have a negative speed, I'm going backwards. If I have a negative speed, I'm going backwards. If I have a positive speed, I'm going forward. So now you have a actual position. So let's define speed. Of speed. Speed is the absolute value of velocity. So speed is the absolute value of velocity. And velocity is the derivative of displacement over t. So let's look at this example. This isn't really an example, it's more of it's showing us what's going on. The graph below, I'm going to show you the graph in a second, shows the graph of velocity, which is f prime, of a particle moving in a horizontal line, as opposed to showing a position of function as s of n. S is a function of t. So what this tells us here is this. At rest, at the beginning, at t sub 0, we're at rest. We're not moving anywhere. As time increases, our speed increases. then if we stay constant, it doesn't move anywhere. As opposed to us going down, slowing down, not linearly, it decreases in a curve. Eventually, what's going to happen here is we stopped. Now, when we move backwards, we're now negative. But why this dip here, since we're going negative, means we're accelerating backwards. So that's why this goes further down deeper. And then this means we're slowing down. So this means we're speeding up going backwards. This means we're slowing down going backwards. Then we stop for a while, catch our breath, and we take off again. So what does that show us? This is the velocity of a particle or an object moving. As we speed up, the velocity increases. As the speed stays constant, velocity doesn't move. Speeds, as we slow down, the velocity decreases. Velocity is going backwards. But remember, speed is an absolute value. Velocity, we can either increase or decrease. If it's positive, we're increasing. If it's negative, we're decreasing. If it's zero, we stop. So you see here that between 3 seconds and 5 seconds, we're going backwards. Between 1 and 3 seconds, we're moving forward, so to speak. And from 6 to 7 seconds, so this is how you interpret a velocity chart. Now, why can we not use this to describe the distance we traveled? Yes, because it's not telling us the actual rate we're moving. It just says for this distance we're accelerating. How fast are we accelerating? We can determine that, but we have no vertical values. All we have is time. And this distance here is greater than this distance, it looks like. So yeah, so we're going backwards further than we're going forward. So yeah, we can't do anything with this information. And the standstill, yeah, and this part here, yes. Nothing happens there. That's very good point. Yeah, we're not given enough information. So those are example 1 and 2. Let's see. Uh-oh. Let me see if we're ready for 3 yet. Oh, no, we didn't, because speed is the absolute value of velocity. So we talked about displacement, we've talked about speed. Speed and velocity are pretty much the same thing. But now we're talking about acceleration. Acceleration is the change of velocity over time. So remember, velocity was a change of displacement of your position over time, how far you moved over a period of time. That's your velocity. Displacement is simply your position. So the change of your position over time is your velocity. The change of your velocity over time is your acceleration. Remember, every time we say change, we're talking about a derivative. So let's define acceleration. Definition of acceleration. Right, then we have to look at the formula for it. Acceleration is the derivative of the object's velocity with respect to time. If a body's or object's position at time t is f of t, then the body's or object's acceleration at time t is the acceleration at time t is the derivative of velocity with respect to time. Let's look at that. So remember, we have our function f of t is our displacement. When we take a derivative of our displacement, what do we get? We get our velocity with respect to t. What happens when we take the derivative of the velocity? We get acceleration. But if we took the derivative of velocity, that means we took the second derivative of the displacement function. So these are how they're related. The displacement, the change of displacement is your velocity, the change of velocity is acceleration. But now, what is the derivative of your acceleration? That's called a jerk. It's the second derivative of your velocity. It's the third derivative of your displacement. And that's what we're looking at there. So since it is a function of t, we use letter J. It equals all that. So you see the relationship between standing or just moving faster, accelerating, and then accelerating your acceleration. These are all changes of with respect to time. Let's look at falling, because that's with the object moving in horizontally. What do we know about an object moving vertically? objects that fall. This is vertical motion. Galileo, about 700 years ago, experimented this. He used the Leaning Tower of Pisa as his place to study, because if you look at the Leaning Tower of Pisa when it was first built, it's a cylinder. What Galileo did is he went up to the top, near the top levels, and he dropped something down. The reason he did that, because if he would have dropped it over here, then you have the wind and everything else. But inside here, it's stationary air. So there's no real changes that occurs to this object. It's the closest he can come to a vacuum, because the only true way you can test the true velocity or true speed of a object falling is in a vacuum, where there's no air resistance. Because if you drop something at the top of Mount Everest, it will fall slower than if you drop it at sea level, because it's lower density and it's further away from the gravity, from the center of the earth. So what we're looking at here, our displacement this is what Galileo came up with. And it all depends on what unit of measurement we use, that it's either going to be American or SAE, everybody else. Gravity is a constant. It's 32 feet per second squared, or 9.8 meters per second squared.
So is it like perfect?
It's
like perfect.
Yeah, well, it's with some small decimals, but yeah, we just rounded it up. Yeah. Again, in the American system, we don't use decimals, so that's why it's not that accurate. That's why the rest of the world uses metric. Even in America, even though we don't teach it, all the engineers, all the scientists use metric system.
Yeah, I think it's all the
Mhm.
That's
Yeah, which is, again, it boggles the mind. We want people to study science, but the basic tools they need to study science, we don't teach the metric system. So it's not that good.
Yeah, because I'm currently 6'2", so it's always used meters.
You're exactly.
So that's why I never heard that they do.
And to be honest with you, when I learned physics in Germany, so I was using 9.8. It wasn't until I came here and somebody was using Americans. I said, no, that's large. But then they were in 32 feet per second squared. So, all right. So let's look at an example here. Okay. And the figure below shows a free fall of a heavy ball bearing. Oh, ball bearing. It's a heavy ball bearing. That's just a steel ball. Released from rest at t equals 0. How many meters does the ball fall in the first 3 seconds? What is the velocity, speed, acceleration when t equals 3?
It's first 3 seconds, right?
Yeah, how many meters does it fall in the first 3 seconds? So after 3 seconds,
Is it like 1 to 3 or it's like what that means? I'm a bit confused. I'm a bit confused. Plus 3 seconds, so it's like 1, 2, 3.
1, 2, 3, yeah,
1, 2, 3, right?
right. At the third second, how far is it falling?
So it's like 5 to 45. That's what it means. Because you want to go 1 second, 1 minute, then the 3 is 45. So it's like that.
Well, let's calculate because these could be wrong. I mean, let's calculate. How do we calculate it? At each one, 1, 2, and 3. So that's what it's asking for. How many meters the ball in the first 2 seconds? So in the first second, it fell this many. Second second, it fell this many.
Oh,
Third
okay,
second,
okay.
it is 1, 2, 3, but it's 1, then 2, then 3.
Oh.
That's the way I interpret it. So how would you do it? What's the formula you're going to use?
What is
We're looking.
distance?
Where's our formula? Yeah. S is equal to 1/2
Oh,
gravity times square
right.
because it's a free falling body. Because it's asking us for a position, which is displacement. So we have to first find the displacement of it. So we have 1/2 9.8 t squared. So at 1, this is going to be constant. It's going to be 4.9 t squared. So 4.9 times 1 is 4.9 meters. So what I'm saying is, so it's not 5, it's 4.9. It's right before there. At 2, we have 4.9 times 2, which is 9.8. No, squared. We have to square it.
Oh, yeah.
So it's 4.9 times 4, 19.6 meters. So it's 19.6 meters. Again, it's not exactly at 20. And then at S3, we have 4.9 times 3 squared, 4.9 times 9, which is 81, 6, 44.1. So during the first 3 seconds, it fell a total of 44.1 meters. That's A. Now, what is the velocity, speed, and acceleration when t equals 3? What formula do we have to start off with? Because we need to find velocity, speed, and acceleration at t equals 3. So what's the velocity? We know also g is a constant, 9.8 meters per second squared. So we can, this 1/2 9.8, we can just say 4.9 from now on. This is always going to be 4.9 t squared. So let's find the derivative of this. Nine point eight t. So when at 3 seconds, we have 9.8 times 3, 27. .4 meters per second. Why is it meters per second? Yeah, because this is meters per second squared, and we take every 1 second. So it's per second. All right. Then what? Then what we're looking for? We have velocity. What's our speed?
Distance divided by time, right?
Is what?
Distance divided by time.
Speed is the difference in, what do you call that? What's that? The displacement.
Okay, displacement.
Right.
That's-
Because it's the absolute value of velocity. The speed is accelerating downwards. So the speed is the absolute value of our velocity. So it's the absolute velocity at 3, which is 29.4 meters per second. So that's number 2. Now we want the acceleration. What is acceleration? It's the first derivative of velocity. Or the second derivative of the speed of the displacement. So our velocity is 4.9 t squared. The derivative of that would be 9.8 t. The velocity is 4.9 t squared. No. No, it's not, because it's just t. It was 9.8 t. That's the velocity. So 9.8 t, the derivative of it is 9.8. It's a constant. Meters per second squared. There's no t. Because we started off with our displacement was squared. We took a derivative of this. Derivative of that, we got this. This is s prime.
Oh.
So the derivative of that.
Just 10%. Because 1 times 10%.
Right. So that disappears, it's 9.8. Okay, let's do example 4. Yes. There. A dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second. As the picture shows. It reaches a height of 160 t, that's the velocity, minus the gravity. How high does the rock go? So this is our height. It's a quadratic equation. So what we can do here factor that out. And set both of these equal to 0. So t is equal to 10. Which means if our time starts at 0 and it's a parabola and it goes to 10 seconds, where's our vertex going to be? Our vertex is going to be at t equals 5. So when t equals 5, our position is 160 times 5 minus 16 times 5 squared. $800 minus 16 times 25. That's 30, 12, that's 15. 5, so it's 0, 0. 700. Oh, yeah. Let me try this.
Yeah, just 8 times 25 is 200 times 16. Yeah, 400.
12, 13, 15. That's 0. That's 0. This is 5. And that's 2. It's 400.
Yeah.
So 800 minus 400, it goes 400 meters in the air, or feet. What are the velocity and speed of the rock when it is 256 feet above the ground? On the way up and on the way down? Well, because remember, our height is 400. So it has to go through 256 once on the way up and once on the way down.
Asking for the between the up and the down part.
It's looking for both of these, how fast they're going, both of those. So we have to first find the velocity and the speed. So let's see, the velocity. Oh, it gave us the velocity. So if we take this equation, so if we say the velocity is the derivative of s with respect to t, we have 160t minus 16t squared. Take the derivative of that, we get 160 minus 32t feet per second. That's our velocity. But we don't need that's what we're looking for. So we need to know, we know the position is 160t minus 16t squared. We want it when it is how high? 256 feet. Because we have to find the t's first to put in the formula. So we have 16t squared minus 160t plus 256 equals 0. So that's, let's see, 256 to 16 go inside there. 1,
So 96 or 36. 6.
yeah, that's nice. Yes, so we can factor out a 16. So we have t squared minus 10t plus 16. So it's going to be t minus 8, t minus 2. So it's going to be at 256 feet after 2 and 8 seconds. All right, so where do we plug that number in? Right here, the calculator, what we just calculated.
Oh, the
Mhm. This is example 4, continue. So we have t equals 2 and 8. V of t equals 160 minus 32t feet per second. So V of 2 and then V of 8.
So it's just a negative. This one is 96 feet, that 2, 96 feet per second. and the other one is negative 96%.
Why is that?
Because other is, going up, and other is going down.
Very good. Because remember our velocities, we can slow down, accelerate, decelerate, or go backwards even. Perfect. Okay.
It's like almost perfect. It's like going in a perfect rate, going this like.
Well, yeah, we're lucky with that because again, there's not looking at wind or anything else. Okay, so it's D. What is the acceleration of the rock at any time during flight after blast? What is the acceleration? The acceleration, remember, it's the derivative of velocity. So our velocity was 160 minus 32t. So the first derivative of velocity is acceleration. That goes to 0. Negative 32. Second squared because the time's gone. Why is that? Because gravity is the only force acting upon it. That's the only accelerated force acting upon it. B. When does the rock hit the ground again? Well, we know our displacement was 160t minus 16t squared. Remember in the first question, we found it equals 0 and 10. That's where we found our. So after 10 seconds, we'll get there. So we have 16t, 10 minus t. I can factor those out. At t equals 10, we get 16 times 10. Okay, now why is that? Oh, the ground hits the ground again after 10 seconds. Make sense?
Why is it okay if you just plug it to the 10 without, simplifying? Like,
Oh, yeah. Actually, we didn't have to do anything because when it asked when, we figured that out in the first part. We figured that out here at t equals 0 and t equals 10. We knew it's going to land in 10 seconds because we factored it out at the beginning. So we didn't have to do all that work. Okay, so that's enough of physics. Now let's look at economics. Because in physics, we always talk about acceleration, velocity, all with respect to time. In reality, we don't need time for everything. Because in economics, you can look at units produced, units sold, the cost per unit produced. So in physics, remember we talked about change meant derivative? In economics, whenever we say the word marginal, that means derivative. So in business, whenever you see the word marginal, marginal cost, marginal profit, then we're looking at derivatives. We're looking at manufacturing. This function is the cost function. Cost with respect to the number of units produced. The marginal cost of production this is the rate of change of cost with respect to the level of production. So this is, since we started off with C of x, this is dc over dx. Again, we're using x, that's x number produced. We're starting off with number of produced x. We want to go to number of increase of production. Yeah, that's horrible. Increase of production. So that's going to be x plus h. So what would the average cost of each additional item to produce. So what would be the average cost of each additional item? Remember, average cost or average is this one. This goes back to what we just did earlier. The average rate of change was f of x plus h minus f of x over h. This is the average cost. C, the cost of x plus h plus or minus of x. So what's the marginal cost? The marginal cost of producing more items per time period. In other words, if you want to increase, if you're an ice cream shop, you want to increase the production of per day, or if you're a car manufacturer, per month or per week. So the marginal cost of those items is the derivative of C with respect to T. Or X, not T, X, number of items. Which is, since it's the derivative, it's the limit as h goes to 0 of cx plus h minus c of x all over h. Again, it's the same thing. Only thing it changes is the industry that uses it. If it was engineering, it's velocity, acceleration, or whatever. If it's business, it's the cost of items, because you want to know what your bottom line is going to be. Let's look at this. Suppose that it costs x cubed minus 6x squared plus 15x dollars to produce x radiators when 8 to 30 radiators are produced, and that R is revenue, is the money you have coming in, equals x cubed minus 3x squared plus 12x, gives $1 revenue selling x radiators. Your shop currently produces 10 radiators per day. How much extra will it cost to produce one more radiator a day? And what is the estimated increase in revenue and increase in profit for selling 11 radiators per day? Where's example 4? Lost example 4. I lost example 4. Oh well. Let's do this one then. So, what do we do first? What is it asking us to find? Right, so how do we do that? We know the marginal change would be what? Well, because we're trying to increase it one more per day. So that's the marginal change of production. No, remember marginal means what? Marginal means derivative. So let's look at the marginal cost of producing one extra one. So we have C of X is equal to X cubed minus 6X squared plus 15X. The marginal cost of increasing, yes, that's the formula. So we started off with 10. How much would it be the cost for producing 10? So it's 300 minus 120 plus 15. That's 180 plus 15 is 195. All right, so then we have to look at this is the marginal cost. Then we have to look at the marginal revenue. So the revenue function is X cubed minus 3X squared plus 12X. So take the derivative of that, we get 3X squared minus 6X plus 12. And at producing 10, so 300 minus 60 plus 12. 300 minus 60 is 240 plus 12 is 252. So that's your marginal revenue. Right. So if we go from 10 to 11, $252 minus 195. It costs $57 per unit for that one.
But it's used general, right?
Hmm?
For the bottom, so
Because we're looking at what it is per one. All right, what we have so far. So this is what it's costing us so far. For with 10, we are it's costing us $195. And we're only making 252. So the profit,
for the 10 is. For
the profit is marginal revenue how much you sell minus how much it costs to make it.
Yeah, so that. Well, that's what we tell, right? Right, that's what setting can really. That's what they want, because something like. Yeah.
Yes, but we don't have to go to 11. If you increase it to 11, you will make a profit of $57.
How then, like, is it like a change?
Because this is what it's so far. This is what it's based on so far.
Oh, the next.
Well, it's costing us this much to make 10. So if we increase it any, for each item we increase it, we're looking at making it that much profit per item. This is our profit after making 10 items
Oh,
and selling 10 items. So if we made 10 and sold 10, that means this is what we have left. It's not going to be $5.70. It's going to be $57 profit per. It's even if we go to 11, if we sell 11, or if we sell 14. Which each one we increase by will make this much money extra.
okay, so it's like each, not.
Yes.
It's not like 10.
Right.
It's not like.
Because now, so if we sell it to 11, we'll get $57. If we sold 2, we'll get 114.
Was like the brain.
Right. It's yes, graded, yes.
I mean.
Okay. You got it? Let me see. This is example. Yeah.
Oh, no.
Oh, yeah. Oh, that's 5. It's a huge difference. Mhm. Okay. Example 6 isn't going to be much of an example because it's a description. Marginal rates frequently arise in discussions on tax rates. If your marginal income tax rate is 28% and your income increases by $1,000, you can expect to pay an extra $280 in taxes. This does not mean that you pay 200 or 28% on your entire income. It just means that the current income level L, the rate in which tax T is 0.28. That's your tax rate. You will pay 0.28 in taxes out of every extra dollar you earn. So it's graduated. So for the first amount you pay some tax. Anything over than that, you will pay 28%. So if you made an extra 1,000, you pay that. So that's only above what you're used to paying. So that's all that's saying. But the next year, you may be in a higher tax bracket, that's where it sucks. Okay, really?
I mean, not me, but
Oh.
the rich people that.
Yeah,
Like a corner above.
it's amazing. And then somehow they know the loopholes, so they don't have to pay taxes.
I think that's where, the famous thing, all rich people, invest in Switzerland banks and stuff like that. Swiss banks or something.
Yeah. They invest, they put the bank somewhere else so nobody can trace it. Yeah, I thought about that. So, but we have to pay our taxes though, not all of it. That's interesting. Take half of your money, put it in an American bank, half your money, put it in an offshore investment bank, and only pay half of that. That's an idea. Okay, this is an example.
That's why they pay so much for the roads, because they don't this kind of process and stuff.
Exactly, exactly. Okay, this topic here is on what's called, oh yeah. Okay, basically sensitivity to change is this. It's the derivative. Remember, derivative is slope. If it's a high derivative, that means it's a very steep sensitivity, it's very sensitive to change. If it's going down, it's it's not that much. So it has to do with the size of the derivative. That's all that tells us. Sensitivity changes, simply look at the first derivative, and if it's large, it's very sensitive. If it's negative or not, it's not. If it's positive, it's sensitive. If negative, it's not sensitive. Okay, so we have to kick stop.
Actually